Hello, so today let's talk about why are integrals and derivatives related. This is not a proof, but this is a good intuition of the fundamental theorem of calculus, part 2 and part 1. So now to understand that, first we need to look at this function. So I have a coordinate grid here, not a grid, but a coordinate plane. I just drew the first quadrant because we just focus on one quadrant for now. And we have a function f of x, just a random function given by this y equals f of x graph here. Now what we'll start by doing is, for example, cut the graph here. All this area under the function f of x is given by another function, let's say g of x, let's call it g of x, right? So that's all of this area. So the area under f of x is given by g of x. Make sure you know that, right? So these are two random functions. We have to figure out how g of x and f of x are related. So now if we use a different color marker, and let's say we cut another section a little further, and this is, let's call this width between the two sections right there, dx. And dx is super tiny. It's basically delta x approaching 0. That's what dx is, right? Dx is delta x approaching 0. Now again, the area of dx would be given by this, right? Now if we look at the area of just this rectangle in purple, we'll see that the area of that rectangle is given by g of x plus dx minus g of x, right? That's going to be the whole area until this line minus the whole area until the blue line, which would give the area of this. Now let's look at another. So this is area of the rectangle, so I'm just going to write area right now. Another formula we have for the area is the height of the area of a rectangle. Since dx is basically 0, this becomes a rectangle, so we're assuming that this is a rectangle. So if we use the area of a rectangle formula, we get the base is dx times the height. We know the height is given by f of x, so it's dx times f of x, right? And both of these are giving the area of this purple rectangle over there. And now all we have to do is basically set these two areas equal to each other. So if we do that, we get g of x plus dx minus g of x, that's this area right here, equals f of x times dx. I should have written f of x times dx here, but let's see. Now all we have to do is divide both sides by dx. So if we divide this by dx and divide this by dx, the dx cancel here, and now we're left with f of x equals g of x plus dx minus g of x all over dx. Great. Now what was dx again? From definition, because of the rectangle thing, so dx was delta x approaching 0. So now I'm going to replace all the dx by delta x. So this equals the limit, because as delta x approaches 0, so the limit as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. Now you might know this definition. Instead of delta x, it's h, but if we look closely at this definition, this is just the derivative of g of x with respect to x. So now we have this, that f of x equals the derivative of g of x by this logic, which just shows that f of x is the antiderivative of g of x, and thus the proof of fundamental theorem of calculus, that the derivatives and the integrals cancel each other. Thank you.